our keynote speaker is already online, so I think we'll just kind of keep things moving along. So I'm incredibly pleased to be welcoming Dr. Steve Robinson, professor at UC Davis and director of the Center for Spaceflight Research. He had a very long and distinguished career at NASA, including working as a science researcher, as an engineer, as a technologist, and as well as an astronaut. So he's kind of worked across the board in all of the things that folks from our consortium touch. So Steve, are you available? Are you there?
I'm here. Good morning. Good morning, El Paso.
Excellent. Welcome. So I'm going to pass it off to you. Thank you so much for joining us.
Thanks for very much. It's an honor to be here, and it's wonderful to be back in El Paso, if only virtually. I'm in Sacramento, California right now. But I'm a fan of El Paso. I love the place and the people. As you may know, NASA conducted its shuttle landing training at White Sands. And so our flight base was in El Paso, and so I went there many times during my 17 years as an astronaut. But now I am a professor at UC Davis, University of California at Davis, which is northeast of San Francisco. And it's a community of about 48,000 students. And I have something I want to talk to you about today that well, I was asked to talk about something called the Home Space Technology Research Institute. Let me share my screen and we'll go over to that. All right, let's just move along. This is not a very long talk, so it's high level. But let's lay some background here. What I'm going to tell you about is a NASA-sponsored Space Technology Research Institute, a 5-year program. We're in year 3, just starting year 4, actually. It's 7 universities, about 75 different researchers, looking at the technology required for deep space habitats. We're not designing the spacecraft itself. That won't be our job, but we are trying to identify, develop, and validate the essential technologies without which the human race will not have a deep space, partially intermittently crewed habitat. So let's talk about that. 3 major flavors that we're thinking of course, microgravity, lunar surface, and Mars surface. About 15 years lifetime, but here's the key, and here's the hard part. Here's the part we really haven't accomplished before. The crew is not there very much. So it has to be capable of life support, but it mostly has to be capable of supporting itself. And depending on where this deep space habitat is, it could have communications dropouts and delays. So fairly autonomous from mission control, at least on the minute-by-minute basis. Very, very different from the picture of that thing you see in the corner, the ISS. I've been there twice. It is a place, and I worked in mission control for about 15 years. ISS is an amazing place. We're just starting its 23rd year of consistent human habitation. And that is a tremendous accomplishment, but it's quite different than the thing we're talking about for a deep space habitat. So the unique requirements is we do need spacecraft autonomy for when the people are there and when the spacecraft is really out of reach of the home team. And learning systems are required. Whatever the spacecraft should be capable of on year 1 should be quite different on year 15. So NASA calls this a SmartHab. What's a SmartHab? Let's start with the goal of any habitat. Keep the crew alive, accomplish the mission objectives. The smart part is, here's the way we have defined it within our institute: a progressively pervasive onboard autonomy. So this doesn't mean humans are, the goal is to replace humans, and humans are optional. What it means is that we have human supervised decision making that is integrated with vehicle self-awareness, and vehicle self-sufficient ability. So it's a teaming. Sometimes the humans will be on board, most times they won't. Utilization of the resources. Resources, of course, are extremely scarce, and resupply is very rarely so. We want to just barely meet mission objectives. Lots of kinds of resources, and again, the habitat capabilities will evolve because the mission objectives and capabilities will too. So such constraints require planning, the essential element. So we enable this planning by constantly estimating the state of the system and predicting its near-term state, but also being able to respond to unexpected events, which are very common in space. Autonomy is defined in a bunch of different ways. We chose the one we like the best in our institute. And let me go down to the bottom one, where autonomous system is an agent or system and comprised of a machine being driven or controlled by some form of autonomy, but the autonomous system always interacts with humans on some level. That's how we think of this SmartHab. Requirements for a deep space habitat that is capable of supporting crew is obviously keep the astronauts alive while they're there, keep the spacecraft alive when they are not. So what we mean by alive, of course, is very different depending on which of those two things we're talking about. Spacecraft, broad spectrum of requirements. It can be fully functional and capable of crew support. It could be partially dormant and so on. But with a crew, with humans, it's a very narrow spectrum. We know this. We know very well what humans in space need to keep alive, and they're very narrow windows of parameter space that we have to work with. So the vehicle has to be able to supply this in a very reliable way. This, of course, leads to lots of challenges, which is why the Space Technology Research Institute even exists. Logistics supply chain, it's almost not there. The maintenance, repair, and overhaul considerations. Well, in space, so many things are a prototype. So you're likely to get surprising behavior. In other words, the requirements for a subsystem may be met on the ground during test, but may not actually be met in flight. You may have early and mysterious failures that were not imagined, which is kind of the norm for spaceflight, especially on a new spacecraft. We won't have the failure and degradation reliable statistics because the ground testing is not the same as the space operational demands. And so in the beginning, we don't have that reliability stats that we usually have. And what's the mean time between failure of something that's never failed? These are challenges. And we have to think about, because of the logistics supply chain is so sparse, the system redundancy in design has to be balanced between what we will stow or build on board with spares for subsystem components. No matter what we do on board, whether it's planned maintenance or response to anomalies, we have to be able to replace parts on board robotically. We could continue this challenges list for a long time. We do internally have a very long list of this. We have to be able to assess and predict the state of the spacecraft at all times and respond to unpredicted events. Humans are involved in the critical decisions. Software has to learn with experience. And this is really important. If you have a semi-autonomous anything, and autonomous, decisions are being recommended, in some cases actually actions taken, these have to be explainable to humans. This is not an easy task. Start with that first one. The spacecraft has to be self-aware. This requires dense and redundant sensor systems, persistent data analytics that happens on board, probably in a non-centralized way. You have to be able to update your sensor systems, move them around, repair them, and come up with new ones as needed. All of this backed up by a dynamic digital twin that we'll talk about a little bit more here. As for the present, modeling the future, of course, as engineers, we know we can have phenomenological modeling based on known state equations or behavior equations of what it is we're modeling. We can have statistical approaches, probabilistic modeling. We can, what you might call observational modeling, where we use machine learning to do classification of behaviors that is not recognizable by human or not modeled, and then must be explainable. And of course, feedback control theory is the basis of most of the controls of the spacecraft, where we respond to errors in the requirements. The digital twin approach, the concept that we envision for a SmartHab, is we do include past information, which is being generated at all times. So it's kind of a library or repository of information, but also an integrated models for defining the current state and developing intelligent prognostics, having a crystal ball for what's going to happen tomorrow, what's going to happen next week, and always be running kind of a what-if engine to think of different states that could happen due to degradations or failures, and respond accordingly. Which we use? Well, the answer is obvious, all of them. Not an easy problem at all. So when humans team with these autonomous systems, it kind of brought up to me, well, maybe this is going to lead to a new requirement for astronaut selection. If the spacecraft is going to be run to an unprecedented degree for a crewed spacecraft by software, especially onboard software, we probably need some onboard software expertise. And then there's the concept of what I call alignment. There is the vehicle state at any snapshot in time. And then there's the vehicle estimation of its state, which we call self-awareness, which is not quite accurate and complete, obviously. And then there's the crew awareness of the vehicle state, which is not quite accurately and complete. So we have three states. How much do we care about those alignment of those three states, and how do we understand the differences or the deltas between them? What about AI learning? How can you stand for your operating system to change every day? Maybe not. So what's the right way to modulate the rate of AI learning for crew acceptability? Crew interfaces are probably going to be adaptable, adjustable, customizable. Same thing with crew procedures. And when we're talking about state estimation and prediction, we also mean the humans. So the spacecraft also has to be self-sufficient. So after self-assessment leads to a decision, then action has to be taken. Well, people aren't there most of the time, so the spacecraft really does require this. And it's mostly going to be a software-driven response to faults. The idea is to be aware of, track, and predict future states of degrading systems, which we all are, so that we kind of drive the surprise out of the whole enterprise. Well, that's an impossible ideal, but that's what we try to do. If we're aware of degradation, it can help us take action before an actual failure occurs. At least that's the ideal. And again, this will require robotic agents inside and outside, but not just those. Inside, I think we kind of know what we need, but we often think about robotic agents operating in the part of the spacecraft where the people are, the part you can see. But where things actually are happening and where things may misbehave, degrade, or fail is actually underneath the floor, so above the ceiling, inside the wall panels, in the racks. And so robotic systems really have to be able to deal with that, both for planned and unpredicted tasks. Deterministic tasks with robotics. In other words, you have something over there, you want to move it with a robot over here and attach it in some way. But what about non-deterministic tasks? I'll get to that in a second. Robot degradation, robots and other systems, so we have to worry about that too. Here's a pretty typical picture of the inside of the ISS. Look at all the flexible stuff. Look at all the flexible stuff. And I think it's going to be that way in the future too. Flexible things are extremely useful in space, and you can't get away from wires and hoses, cables. So how do you robotically manipulate those things? Turns out that's a very difficult thing to do. We've been working on it within the home project. Here's a case where we have 2 robot arms. This is very simple. The robot arm on the right, I'll show you this in a sec. Robot arm on the right is trying to pick up this box from a wall. But there's a depth sensing camera that says you've got a wire in the way. You can't do that. The robot arm on the left actually does a very fast real-time modeling of the wire, calculates where to touch it, how much to move it, reaches out, pulls it out of the way, and gives arm number 1 to go to proceed. I'll show you 2 videos that do that. And I'll try to show you 2 videos. I'm just pulling it off my disk here. Or maybe not pulling it off my disk. There we go. Okay, there's the pink wire. There's the modeling has been done. That little gap was to wait for the modeling to be done so that the left arm would know how much to move the wire, and then the right arm can go in and grab that orange box. You can take a look at it from a different point of view here. Different wire configuration. Oh, the wire's in the way, better move it. How much? Let's model it. Move it out of the way and go to get the orange box. This looks simple. You could teach, a 4-year-old to do this. It is not simple because robot arms do not have the innate intelligence and learning capability of a 4-year-old. So this has been a very interesting, demanding, and exciting aspect of the home robotics research. This manipulation of these flexible objects. We're not the only ones doing things like this, but we feel like this is one of those things you can't have that SmartHab, that deep space habitat that we want without having this kind of capability. On the outside, I think we know about the outside, so I'm not going to talk about it too much. Although one of the things we're doing is developing a free-flying inspector, whose arms may only be able to reach so much on the spacecraft. And we envision a disposable CubeSat that is deployed on need and does very low kinetic energy, relative kinetic energy inspection of the outside on demand. Well, that lays out kind of the need, kind of the background and foundation that led NASA to say, we'd like an outside group of researchers to come up with some ideas for technology and validate them in an integrated sense that we can choose from when we think about designing a deep space habitat. So there are 2 space technology research institutes that started at just about the same time. One led out of Purdue, called Foresee, and one out of UC Davis called Home. We named it Habitats Optimized for Missions of Exploration. There are 7 universities involved here. You can see on the right. We have an org chart, as usual. I'm the director. Industry of affiliates of Blue Origin, Sierra Nevada, and Collins Aerospace. And the mission, everything I just said, really. And the spacecraft, as usual for these systems, has to be able to sense, make a decision, and act on it, and then check that the new state approximates the desired state. Strategic goals: build the research team with NASA and industry, generate the validated low technology TRL that we're talking about, and most importantly, educate the diverse population of future aerospace leaders in spacecraft research. One thing we did not do, which was to reach out and build our team just out of aerospace professionals. We thought that if we want different ideas, new ideas, we need to go into civil engineering. We need experts in machine learning, of course, systems engineers to integrate this. Industrial design, industrial robotics, human systems integration, architecture, logistics planning, digital twin technology. And of course, when you build a team like that, the first year or so is spent learning to speak each other's language. And so that's been really exciting. We're just starting year 4 now. top level requirements, everything I've just been talking about really. And I think, one of the keys is you have to be able to down mode to some sort of more quiescent state when the crew is not present. But when the crew comes back, you have to know that the spacecraft is human life, capable of supporting human life well before they get there. In fact, probably before they launch. I think this kind of our home philosophy is to meet the requirements I laid out in the first part of my talk here. One thing I'll point out here is not just we have machine learning and human demonstrated learning, but also humans will learn from trained software too. Assumptions and constraints. Let me just go to that main part in yellow there, where every spacecraft has planned reconfiguration, but every spacecraft also has unplanned reconfiguration. In other words, its current state changes in a way that was not built into the original design. So you have to be able to be aware of that, be able to predict, so okay, where are we going? What's going to happen next? What's the vector of degradation or change? And then respond to it in some way if required. And we're interested in using only the autonomy that we need, and we understand that the autonomy will never be enough. So we're always going to have human involvement. We're not trying to drive humans out of the system here. We're trying to make humans more capable, more safe, more aware of the spacecraft that they're in, and more able to meet mission objectives. And of course, MCC Mission Control Center will not be what we're used to in the ISS world. Plan configuration, I'm going to zoom right through here because we kind of know that the spacecraft evolves as it's up there, and it'll happen with or without the crew. But the unplanned configuration, I think the key for us in home is recognition of degradation, as I've mentioned several times. So trying to detect, model, and predict future states of degrading systems is very much a challenge. And then there's, of course, failures, errors, emergent behaviors. In other words, the subsystem is actually a different subsystem than we thought it was. And there are things that will fail and we won't be able to either explain or recover from. So this will require various types of intervention, including manufacturing replacement parts on board and certifying it. So these actions and unplanned reconfigurations will definitely challenge both the humans and the autonomous systems. So, summarize home here. We're looking at self-awareness of the vehicle, human autonomy teaming, and self-sufficiency. So to do this, we've come up with 5 technology themes. A vehicle functional design, where we're not designing the vehicle, but we're defining what the vehicle should do in 2 different design reference missions. One is lunar surface, and the other one is microgravity. Self-awareness, we've talked about. Human autonomy teaming, we talked about where the humans may or may not be on the ship. Self-sufficiency, and the digital twin, the newer idea we've had. Certainly not going to go through this, but this has led to about, I think the number is at 40 internal research projects that are scattered through the research thrust, but now we're starting to integrate them with this technology maturation roadmap we have here, and we are just starting year 4, so we're right about here, and we are defining and assembling this integrated technology demonstrations so we can actually validate what we've come up with. We have a number of different demonstrations. As you can see, fairly operational tests of our technology, whether it's modeling or physical parts that are moving, usually integrated together. And we have 2 habitat mock-ups, one at CU Boulder and one at UC Davis, in which we can do this, and several robotics labs too. Our demo roadmap, won't take you through all of this, but basically we start with single projects. We try to validate those technologies in the projects, And we integrate them into what we call a capability demo. And then in the last year, we'll have 3 different kinds of capstone integrated simulations, a la NASA Johnson, and that red circle is about where we are now. I mentioned one of the most important products of a big project like this are the students. Where have the students gone after they've graduated, when their research was within the home project? And as you can see, in 3 years, there's been lots of success. I think the home project is definitely meeting its objective in this sense. And of course, the students are the lifeblood of the working fluid of a project like this, and they have a very strong community. Well, I hope I've given you just a little bit of taste of what the Home Space Technology Research Institute looks like from the point of view of our big team led by the UC Davis folks. So thank you very much for your attention. And I don't know if we have time for questions or not, do we?
Yeah. Can we get, we do have time for a couple of questions. If folks want to put them in the Slido, if you have questions for Steve. I'm not seeing any up here yet. If there are questions in the room and you don't have Slido on, I could repeat them. I hate to do that, but what's that? Okay, so I do have a question from Nikki in the room. Do the two, how do the two STRI, so Space Tech Research Institutes, work together?
I was hoping you'd ask that. When we started, we actually didn't know about each other. So it was not set up to work together. But of course, we're all working on somewhat similar things in totally different ways, which is exciting. The Purdue-led RETHI Institute is looking at kind of a system of systems, total modeling in Simulink of a habitat, and their theme really is resilience. Of all the things that could happen to the spacecraft, how can it respond in a safe way and still accomplish mission objectives? As you see, the Home Institute is starting more from the inside out, working from the inside out, where we develop technologies and then we integrate them further and further and further and model as we go. I think the digital twin idea, we've advanced it in a way that's a little different than has been used for aerospace before. So there are similarities and differences. So 2 weeks ago, the two institutes got together for 2 days in San Antonio, Texas, actually, and discussed what we're doing and how we can integrate our work as we go forward in the final couple of years. I mean, great time, good presence by NASA there, and we have I think we're going down the road kind of hand in hand, is how it is. We're not fully integrated, nor should we be, but we certainly have a complementary way of approaching things.
Excellent. A couple other questions popped up. I'm going to ask one to you, and I think the other one might be a question that needs to save for Nikki or Jim later on. So the question is, a lot of the approach seems similar to the approach for Gateway. Are you working with them at all to share insights and lessons learned?
Yeah, we sure are. We're Julia Badger, in fact, is the technical monitor for the other STRI, but we're closely in touch with her and some of the other Gateway folks. We have things that Gateway doesn't have and wish they had, such as internal robotics, which Gateway did have, but no longer does. I think our technology will not be used on Gateway. Gateway is so far down the road, based mostly on current technology. But if you thought of what Gateway would, a future spacecraft beyond Gateway would be this SmartHab, this home approach to SmartHabs. So yes, indeed, we are definitely thinking of it as a jumping off point and working with the Gateway folks to stay aware.
Okay. Now, of course, the questions are pouring in. Do you have time for one or two quick more ones?
Oh, I do. It's you that might be a little short.
Okay. Okay, so you showed a simple robotic example. How rapidly do you think robotic learning or decision-making capabilities will progress with increasing complexity?
Very rapidly and not rapidly enough.
That's a great answer.
Yeah, but you know what I mean. I mean, demonstrating something in a lab is one thing. Having something that is reliable enough to use in a safety critical application, especially with time is short and people may not be there and may not be aware of it, every little detail. We've got a long ways to go to that. We really do. There's going to be a lot of work to do, and you know, especially when you have learning in a system, it means the system won't operate exactly the same way every single time. What are the implications for that in terms of predictability? So there's a lot to think about.
Okay, and one more quick one before we hand it off to Nikki. For the flexible manipulation tasks you were mentioning, are you modeling the properties of the flexibles, so cables, et cetera, in order to know how far they can move?
We are, but I wish we weren't. It's a you know, a typical mass spring damper model that is done in real time very quickly. So it's the depth sensing camera generates a point cloud, which is then volumetrically filtered to generate a to spline fit a curve that represents the cable. Then we segment that curve and model each segment with a point spring damper system. And then we say, which way do we want it to go? We pick the location based on some rules where we should actually touch it and what is the displacement vector that we should take. And most importantly, the model will tell us how far we can go without stressing the cable. So we actually put a stretch limit on it. Now, I would rather not do all that. I would rather use a force moment sensor on the end effector of the cable and do what that 4-year-old would do and just say, hey, would you get that out of the way and don't push it too far. So that's where we're trying to go.
Okay, I think that's all we've got time for right now. There was one final question about whether people can get involved with the work that you're doing. So I think we'll try to address that offline if possible. And before I hand it off to Nikki Werkheiser, our fearless leader at Space Tech, I do have a couple comments from